Hi guys, in this lecture we will be starting our study about the power electronics. So basically the course of power electronics has been divided into some units. First unit is power semiconductor devices. Second unit is rectifiers. Third unit is choppers. Then inverters, and then AC voltage controllers. Now in this year course, AC voltage controller does not appear in the GATE course. So we will be focusing our attention mainly on the first four concepts, that is power semiconductor devices, rectifiers, choppers and inverters. The recommended book for this topic is P.S. Bhimra. It consists of good theory as well as some numerical examples and unsolved problems. So you can go through that. Otherwise, the question bank that has been provided to you contains selected questions which are very good for your practice. So now let us get started with our power electronics course. So in this lecture what we will do is, we will first take a look at the basics of power electronics or prerequisites of power electronics. Now first question that comes to mind is, what is power electronics? Now if you see in our electrical engineering branch, what are the major subjects? First one is your electrical machines. Now what does electrical machine deal with? It deals with electromechanical power conversion, that is conversion of electrical energy into mechanical and vice versa. Then the next subject is power system. Now power system deals with generation, transmission and distribution of electrical energy. And then it is power electronics. In power electronics what we study is, we study about the conditioning and control of the electrical power. That is, we will say that power remains constant but we wish to change the voltage, current, frequency and form that is AC or DC. Even if the power remains constant, that is, it does not amplify or attenuate the power, then also I want to change certain parameters like the level of the voltage, amplitude, frequency of the voltage, or even change the form whether from AC to DC or from DC to AC. That is done by means of power electronics circuit. Now power electronics branch is the most advanced subject in our electrical engineering, and most of the research goes on in the power electronics. What is the research all about is, the research is to develop power electronic converters which have high efficiency and yet they operate at a lower cost, and they must have high rating. Now there are two branches of electronics. One is your signal electronics, other is your power electronics. Signal electronics basically deals with your analog electronics and digital electronics. Now signal electronics has usually voltage level plus minus 15 volt, which is the supply voltage for op-amp. Here the voltage in power electronics is in the order of kilovolts. Okay, and then here the current is from microampere to milliampere. Here the current is from ampere to kiloampere. Here power is from milliwatt to watt. Here power is from watt to kilowatt. That means power electronic devices, they only have the higher rating as compared to their signal electronic counterparts. That is, a diode will have a counterpart in the power electronics which is your power diode, and the difference between a signal diode and a power diode will be, power diode will possess much higher rating as compared to your signal diode. So power electronics is nothing but application of the electronics principle, the principles that we study in analog electronics, to the power domain. Okay, power domain means using the electronic equipments at much higher rating. That is the basics of the power electronics, and that is what is the necessity of the power electronics. Now here we have taken an example of a power electronic circuit. So this is a source which will be a machine. It will generate electrical power. Then there will be power processing circuit which will control the voltage and the frequency of this output, and then we will deliver it to the load. But now if you are controlling the power, then always closed loop control systems are more accurate as compared to your open loop. So we need certain feedback which is implemented in terms of this control circuit. So this control circuit does what is, it measures the load parameters and then it controls the switching of the power processing circuit. What is meant by switching of the power processing circuit is, this power processing circuit is made of different type of switches. So this control circuit will control the state of different switches, which switch will be on and which switch will be off, based on the parameters at the load side. Okay, so that is how different power electronic converters are implemented, and some of the power semiconductor devices are thyristor, power diode, power BJT, etc. Okay, so whatever devices have their signal counterparts, they will be associated with one additional term, that is power. Diode will become power diode, BJT will become power BJT. Now it is clear to me that I want to change the frequency, I want to change the voltage level. But what the question that comes to mind is, why do I want to do so? Though this question might seem silly, but it actually necessitates the application of the power electronics. What is the application of power electronics in our real world scenario? Now, first is, if you can control the voltage and frequency of the output of any system, then that system can be used to drive a DC or a AC motor. Now suppose I change the frequency, then synchronous speed changes 120 into F by P. If synchronous speed changes, then the speed of induction motor will change. If we have somehow variable frequency, it will have variable Ns, and hence Nr will be variable, which is equal to Ns into 1 minus S. So that means we can control the speed of induction motor by varying the frequency using power electronic converters. Similarly, variable VDC can cause variable speed in case of DC motor. Okay, to control the DC motor, one of the methods is armature voltage control method, and in armature voltage control we control the terminal voltage of the DC motor. That can be controlled by the use of power electronic devices. Okay, and in the DC motor and the induction motor, usually induction motor is cheaper as compared to your DC motor, and its maintenance is easy. But the methods involved in controlling the speed of induction motor are more complicated as compared to the methods involved for the DC motor, because in DC motor if you change the supply voltage, it will change the speed. But in induction motor there are techniques like pole changing technique, variable frequency drive, such sort of techniques, so it is more difficult. So that is one application in terms of electrical machine. Next application comes with regards to the power system. Now what is the application in power system? It is used for reactive power compensation. That is, it can generate reactive power by means of devices like thyristor controlled reactor, thyristor switched capacitor, and static compensator. These will supply reactive power which can control the voltage at any bus. And SVC is also an example of power electronic applications. And when we studied power systems, then what we do is, there we apply SVC to clamp the voltage at any bus as well as improve the stability of the system. We saw that Pmax became 2 times Pmax initial. Okay, that is in the case for the power systems. Is it fine? These devices are called as FACTS devices, that is flexible AC transmission system. Because if you want to change the power carrying capability of AC, then we make use of these devices which can change the value of Pmax and hence the power capability of AC. Next application comes in transportation. In transportation also we use electrical motors, like in traction we use DC series motor, and in many railway cars we use induction motor. There, to control the speed, we can make use of the power electronic converters. Then low power application. If you want to control the speed of the fan, then fan also consists of a single phase induction motor. Then that means we can control the speed of fan by means of power electronic converters, because they can help us in controlling the speed of induction motor. And the last is renewable sources. Now renewable energy sources like solar cell and solar panel, they generate the DC power, but the power required for utilization is usually in the form of AC. So the conversion from DC to AC is done by means of power electronic converters. So these are many applications of the power electronic converters. That is why it is an interest area of the research. Now, what are the advantages of using power electronic converters than the conventional method of power conversion? First thing is no rotational loss. Power electronic devices are always static in nature, that is, they do not move, and hence their rotational loss will be 0. Since there is no rotational loss, efficiency will be high. That is one of the biggest advantage of the power electronics, that power electronics converter have high efficiency. Otherwise, one of the methods to convert AC into DC could be take 3-phase AC, apply it to an induction motor, which will give mechanical power, which will be coupled to a DC generator. Then it will give the DC output. But the thing is in that in both the machines we will have rotational losses, so efficiency of conversion will be less. Whereas if we use a rectifier to convert AC into DC, then the efficiency is very high. Due to this fact, the DC generators are obsolete nowadays, because if you want to generate electrical output as DC, then you can better convert AC directly into DC by means of power electronic converters. Now, if rotational losses are not there, heat reduces, due to which temperature reduces, due to which cooling requirement also reduces. If cooling requirement also reduces, due to which we make use of heat sink with the power electronic switches. That is, power electronic devices are always mounted on a heat sink, which will dissipate the heat generated in the power electronic device. If it can dissipate the heat generated, then no need of additional cooling methods to cool down any device. Next is compact in size. As I told you, when we convert power from one form to another using machines, there will be two machines which will increase the size of system, whereas the size of power electronic converter can be as small as that it can be held in hand. Okay, so they are very compact in size. Next is that we can implement closed loop control. Now, why closed loop control is possible in power electronics? Because of the 3-terminal devices. Now, usually the switches that we use in power electronics have 3 terminals. 2 are used to carry current from one point to another, or 2 are called as power terminals, whereas one other terminal is called as control terminals, which controls the power conversion. So whatever control signal we were feeding in the power processing circuit, that will be fed to the control terminal. Whereas in case of electrical machines, we only have 2 terminals, which are actually the power terminal. So to control the speed or to control any parameter, you actually have to change the quantity at the power terminals. You do not have any additional control terminal. So that is also one of the advantage of the power electronics. Now, what are the disadvantages? The biggest disadvantage, always remember, in power electronics is harmonics. Now, what happens due to switching? That is, switching on and off, harmonics will be induced. Let me take an example. If we switch on and off a constant current, it will generate a square wave form. Now, this square wave always has harmonics because it is not sinusoidal. What is meant by harmonics is, Harmonics are the multiple of fundamental frequency when any function is expanded as a Fourier series. Now suppose this is I. If it is expanded as a Fourier series, sigma n is equal to 1 to infinity an cos n omega naught t plus bn sin n omega naught t, then the terms which have any term that is except n is equal to 1 will be harmonic. The only desirable term is the fundamental, due to which harmonics are generated in the power electronic converters. So due to switching operation, most of the waveform in power electronic converters are non-sinusoidal but yet periodic, and hence they will have harmonic content. And if we were converting using the machines, then there would be no harmonics induced in the system. So that is the biggest disadvantage. But the question that arises in our mind is, now I know that there are harmonics. So the first question that comes to mind is, why remove harmonics? What is the disadvantage of harmonics? Now, the RMS value of current with harmonics will be under root I0 square plus half I1 square I2 square, go on up to infinity. Now this is the amplitude of fundamental, amplitude of second harmonic. So this is my fundamental term, which is desirable. Rest of the terms are undesirable, which means that RMS value of the current increases due to harmonics in the system. If RMS current increases, then the losses, which are equal to IRMS square into R, they will also increase. So copper losses increase due to increase in RMS current of the system. Similarly, harmonics have a frequency of n omega naught or nf, due to which harmonic frequency is high, due to which core losses, which are proportional to frequency raised to the power n, in eddy current case it is square, in hysteresis case it is 1.6. So they will also increase. So core losses will also increase, which reduces the efficiency of the system. Also the impact lies on the power factor. Now suppose I consider a power electronic converter as 100% efficient. That means whatever is the input power will be same as the output power. Now input power will be Vs Is cos phi, where Vs is the supply RMS voltage, Is is the supply RMS current. P0, suppose it is DC output, V0 I0. So cos phi will be V0 I0 by Vs Is. Now as I told you, RMS current increases with increase in harmonics. So cos phi reduces. So it reduces the input power factor of the converter. If input power factor is reduced, that means the supply power consists of reactive power content, which is high, and it is undesirable. That is why power electronic converters require reactive power to operate, which in case of HVDC is supplied by means of compensators. Okay, in HVDC both terminals have power electronic converters, so they will be connected to the compensators. Otherwise, they will reduce the power factor of the supply side. Now, when we start the study of power electronics, first thing that we need to understand is Fourier series, because here a lot of waveforms will be encountered which will be non-sinusoidal, and to analyze the behavior of any converter, we will need to extract the harmonics, for which we need to extract the Fourier series. Now Fourier series is defined for periodic functions, and here we are interested in trigonometric Fourier series, which expresses any function as a0 plus sigma n is equal to 1 to infinity an cos n omega naught t plus bn sin n omega naught t. Now here a0 is called as the DC or the average value. It is equal to 1 by t integral 0 to t, or let us say t, ft dt. Now if we wish to change the variables into omega naught t, we know that omega naught is 2 pi by t. So omega naught t is 2 pi. So if you multiply and divide by omega naught t, it will be 1 by 2 pi. Integration will be over an interval of 2 pi ft d omega naught t. This will be my a naught. That is the DC, or the average value of the Fourier series. Now the next coefficient, which is an. An is written as 2 by t integration over t ft cos n omega naught t dt. Again multiply and divide by 2 pi, sorry, by omega naught. So it will be 2 by 2 pi ft cos n omega naught t d omega naught t. Similarly, Bn will be 2 by t ft sin n omega naught t dt. If we convert it into omega naught t, it will be 2 by 2 pi integration over 2 pi ft sin n omega naught t d omega naught t. So these are the formulas which are used to derive the Fourier series coefficient. Now there are some properties of Fourier series that must be always kept in mind is, if the waveform is even function means ft is equal to f of minus t, then it implies Bn is 0. Only a0 and an are non-zero. Okay. And if it is an odd function, that is ft is equal to f of minus t, like this, then it is an odd function, then only Bn is non-zero, a0 and an both are 0. If it is half wave symmetric, that is minus ft, then only odd harmonics exist. Odd harmonics means n is equal to 1, 3, 5, 7, like that. Only these terms will exist in the Fourier series expansion. Now let us look at a few of the Fourier series that we will commonly encounter in our power electronics study. So whenever I will encounter these waveforms in future, I will directly use the results obtained in this lecture. So the first waveform is something like this, which remains at V from 0 to pi. So V0 is V from 0 to pi and minus V from pi to 2 pi. Now this is a periodically square waveform, and if we draw it before 0 like this, now how I am drawing it is, I am just repeating the pattern: negative, positive, positive, negative, negative, positive, like this. That means it is symmetrical in first and the third quadrant, hence only, sorry, it is actually odd function, so only sign terms will exist. So we just have to calculate Bn. Is it fine? Since it is odd. Now if you see, if you take an angle theta, the value at it is pi. If you take a value at pi plus theta, the value is minus V. So f of theta is equal to minus f of pi plus theta. Hence it is half wave symmetric, only odd harmonics will exist. Okay, so it will have sign terms with only odd harmonics. Now let me derive what is the Fourier series coefficient. So Bn will be 2 by 2 pi. I am integrating in terms of omega naught t. From 0 to pi it will be V into sin n omega naught t d omega naught t minus pi से 2 pi V sin n omega naught t d omega naught t. Why minus? Because it is minus v. Now let me take this v common. It will become v by pi. Integration of sine will be minus cos n omega naught t by n from 0 to pi. Minus minus will be plus from pi to 2 pi. Now if we substitute the limits, so this will be, let me take out n common, v by n pi, then 1 minus, because cos of n0 is 1, plus minus cos n pi. Now cos 2n pi, that is cos 2 pi, 4 pi, 6 pi will be 1. Now if n is even, that is 2, 4, 6, then cos of n pi will be 1 and bn will be 0. If n is odd, cos n pi is minus 1. So bn is 4v by n pi. So the Fourier series can be expressed as since only odd harmonics exist, sin n omega naught t. So remember this Fourier series specifically as this waveform is actually output voltage of a single phase full bridge inverter. Okay, so there also we will use this Fourier series that we have derived just now. Next, let us move on to another waveform. Here this is actually the input current of single phase semi-converter. Semi-converter means semi-controlled rectifier. So this angle will be pi. So it is going from alpha to pi, then pi plus alpha to 2 pi. Now 2 pi is identical to 0. So this will be drawn like this. Now if you see, this is neither even nor odd because it is not symmetric in first and third quadrant and nor in first and second. So here we will have to calculate an as well as bn. But a0 I can directly say 0 because area will be 0. Positive area is equal to negative area. So we just have to calculate an and bn. So first let me calculate an. It will be 2 by 2 pi integral alpha to pi I cos n omega naught t d omega naught t plus minus I from pi plus alpha to 2 pi cos n omega naught t d omega naught t. So that will become I by pi. Integration of cos will be sin n omega naught t by n from alpha to pi minus sin n omega naught t by n from pi plus alpha to 2 pi. N can be taken as common, I by n pi. This will become sin n pi minus sin n alpha minus sin 2n pi plus sin n pi plus n alpha. Now if you see this waveform actually, if you take an angle theta after 0, the current is I. If you take pi plus theta, the current is minus I. Hence it is half wave symmetric. So odd harmonics only exist. Even will become 0. So if n is equal to even if we put here sine 2 pi, 4 pi, 6 pi will be 0. This will also be 0. Sine n alpha, then sine 2 pi plus something is sine theta. So this will get cancelled with the sine n alpha term. So an is 0. What if n is equal to odd? Then this term is always 0. But these two terms will become identical. So it will be minus 2i by n pi sine n alpha. Okay, because these terms will get added. Now let me calculate Bn. 2 by 2 pi, then alpha to pi I sine n omega naught t d omega naught t minus pi plus alpha to 2 pi I sine n omega naught t d omega naught t. So it will be I by pi, integration of sine is minus cos. So this will be, okay, minus minus will become plus, so I can write okay. So n can be taken as common, I by n pi now for n is equal to odd, this cos n pi will be minus 1, cos 2 n pi will be plus 1. 1 plus minus 1 is 2. So 2 taken as common, this will be 1 minus cos n alpha. Because if n is odd, cos of pi plus theta is minus cos theta. So minus minus will become plus. This term and this term will get added. So 2 can be taken as common. Now since we have an as well as bn, let us combine it into a single Fourier series. So Fourier series will be n is equal to 1, 3, 5 up to infinity. An is minus 2i naught minus 2i by n pi. Then sine n alpha, then cos n omega naught t plus 2i naught by n pi 1 minus cos n alpha sine n omega naught t. Now to combine these two terms, first I can take 2i naught by n pi common. Then this sine theta can be written as 2 sine theta by 2 cos theta by 2. Similarly, 1 minus cos theta will become 2 cos square theta by 2. So what I will do is I will take rather 4i naught by pi common. Okay. Here it is coming sine theta by 2 cos theta by 2. Here cos square theta by 2. So let me take cos theta by 2 common. Then this term will be written as sine n omega naught t. 1 cos theta by 2 will remain. Minus this can be written as cos n omega naught t sine theta by 2 will remain. So this will be 4i by pi cos n alpha by 2 sine n omega naught t minus n alpha by 2. This will be the Fourier series for this waveform. Now let me show you a simpler method to derive this Fourier series. Since this is a very tedious method, I will define a new function. Let me say xt. This xt I am drawing something like this. First see this. Alpha by 2, pi minus alpha by 2, pi plus alpha by 2, then 2 pi minus alpha by 2, minus alpha by 2. So what I have done actually is I have shifted it by left by an angle alpha by 2. So what I can write is xt is equal to I t plus alpha by 2. We have shifted by an angle alpha by 2. Or we can say that it is equal to xt minus alpha by 2. That is we have to shift xt by an angle alpha by 2 towards right to obtain it. So now if you see, this function is an odd function, so we just have to calculate bn. No need to calculate a0 and an. So this will reduce our task, and then we will replace omega naught t by omega naught t minus alpha by 2. So if you derive bn, it will come out to be, or let me say Fourier series directly, xt will come out to be sine n omega naught t. So to derive it, we will replace omega naught t by omega naught t minus alpha by 2. So what we will arrive at is like this, n omega naught t minus n alpha by 2. So this can hugely reduce our task. Moving on to the next waveform. This waveform actually represents input current of a single phase full wave rectifier or single phase full converter. Okay. Now let me apply the shifting principle to obtain the Fourier series to reduce the task. Now if you want to apply the shifting process, then we have to shift it in such a manner that we can arrive at a odd or a even signal. To arrive it at a odd signal, what I will do is I will define x something like this. Okay. So this will be pi, 2 pi. So actually xt will be equal to it plus alpha if we shift this by left to by an angle alpha, or we can say it is equal to xt minus alpha. That is, derive the Fourier series for xt and then shift it by an angle alpha. Now this is the waveform that we saw earlier also, the first sample. So the Fourier series of xt will be sigma n is equal to 135 4i by, since amplitude is replaced by I, sin n omega naught t. So the Fourier series of it would be sigma n is equal to 135 will remain same, 4i by n pi sin n omega naught t minus n alpha, because we will replace omega naught t by omega naught t minus alpha. So n will get multiplied. So this is the Fourier series which we can arrive at in single step instead of doing the tedious calculation. So let me summarize what we covered the basics. We first saw what is power electronics. Then we saw the applications. Then we saw advantages, disadvantages of the power electronics. Then we saw the Fourier series concept, and we saw some of the Fourier series that we will encounter in power electronics course throughout the syllabus. Okay, that is, we will encounter these waveforms in mostly the chapters of rectifiers and inverters. So in the next lecture, what we are gonna do is we will start with the study of power semiconductor devices by first studying about the switches, because in power electronics all semiconductor devices will work in switching mode.